Good. There you go. We are on. Hello, everyone. Okay, we got a minute. Is anyone on? Anyone on? Hello? Hello, hello, hello. Anyone? All right, no one in the chat so far. No one in the chat. Not good. Yeah, there's like a couple second delay. I forget about that. Hey, X Baker, how are you? Hey, Regale33. Hey, Flocka. Hey, Data Guru. Hey. All right, we got some viewers on. Okay, thank you. Okay, we got a minute. Mic check. Audio check. Video check. Check, check, 1, 2. Hey, Stolfy, how are you? How are you? Hello. Okay, mic check. Video check. We sound okay. Are we good? Are we good? Are we good? The light is on. Today's going to be a pretty dense, pretty long topic today. We're gonna need all the time that we can. Hey, thing oscillator. Okay. Hey, crispy nuggets, how are ya? All right, we gotta get started right on the dot today because it's a long topic, and it's gonna be hands-on, of course. Hello, everyone. I'm Ming Chao, an associate teaching professor at Tufts University. This is season six of my security course on Twitch. And today, probably one of the we may have some special guests later on today. We're gonna need the entire hour and 15 minutes today. We're gonna talk about passwords, the wrong ways of storing passwords, cryptographic hash functions, and drum roll, password cracking. Oh yes, password cracking. So what I want to do to start off is to show the wrong way of storing usernames and password on a system. I want to show you that get that started, and that will set up our session for the remainder of today. So we have some users on right now, so I'm going to create a database table of users. Okay, so this database table of users is going to have, just going to say, to make it simple, 2 columns: username, password. Okay, so I'm going to make some usernames here, and I'm going to pick a few people from the audience today. Crispy Nuggets. Crispy Y Nuggets. Sorry, my bad. We got Crispy Nuggets. Okay. I'm going to give you I'm going to make up a password for you. Okay. Well, I'm going to make up a password, okay? Alright, that's going to be your password. Alright, think oscillator. Okay, EMC2. A Stolfy, your password is going to be, money is the most important thing in the world. Okay. I'm gonna add a couple more users. Data Guru 18. Okay, I'm gonna give you a password of okay, Flacaba, Flaca, your password is going to be there you go. Now I'll do one more. Now actually we'll do two more. We go 33. Your password is gonna be, okay, and we'll do X Baker. And X Baker, your password is going to be ABC123 as well too. Okay, so here we go. Alright, so here we are. Here is a fictitious database table of users. Only two columns, username and password. Now just make an assumption here that the database got broken into and someone stole a list of username and passwords. There we go. So an attacker comes into a system, steal the database table of users, and this is what the attacker sees. Tell me what's wrong. What's wrong? There's actually, you can say there's a couple of really obvious problems. So an attacker steals this database table of users. Hey, this happens every day around the world. There you go, as X Baker said. Okay, problem number one is passwords are in plain text. The problem is the passwords are completely in plain text. That is problem number one. That's the biggest problem of them all. So, extremely wrong way, number one, of storing credentials on a system is to store them in plain text. And you don't believe how many companies and people actually do this. I mean, this was done for, it's getting less and less at least. There are still people and companies that still do this. You hear about it on the news every so often. This is just plain bad. Furthermore, if you actually see the passwords in plain text, you hear in this example, actually, we see that there are two people that share the same exact password. Data Guru 18 and X Baker, you both share the same password of ABC123, which is extremely weak. So you really got multiple problems here. Okay, so this is the wrong way, number one, and an extremely wrong way to store passwords on a system in plain text. This is bad. This is really bad. So how can we improve on this design? How can we improve on this design? Well, okay, so the biggest problem we need to solve is we don't want to be storing passwords as plain text. We don't want to have this as plain text. Now, is there another way? Is there a step up? Is there a better way to, just don't store the password as plain text? The answer is yes. And this is where the idea of cryptographic hash function comes into play. A cryptographic hash function is a one-way function, okay? Now, for those of you who have taken a good data structures course in the past, tell me the four important properties. There are four, more than three. Four properties, at least four properties of a good hash function, of an ideal hash function that is used for a hash table. As you remember, a hash table in data structures is used for searching really fast. So, if you have taken data structures in the past, okay, what are the important properties of a hash function, a cryptographic of hash functions? Okay. Okay, 1, 2, 3, 4. All right, come on, tell me. What are the important properties of a hash function? Yeah, they're pretty cheap to compute, okay? Generally speaking, okay, it's a function, okay? They're relatively cheap to compute. That also means it's really fast as well, too. We'll put that as a fifth one. Collision free, okay. No collisions. That means, okay, for each in every unique data, there is always going to be a unique output. So here, for those of you who don't know what a hash function is this. Hash function of input is going to give you what they call a hash value, also known as the output. So you don't want to have any collisions. For each and every unique input, there's going to be a unique output. Two different inputs cannot share the same output, cannot share the same hash value. That's a collision. Two people cannot share the same dinner. That's an important property of a hash function. Number two, yeah, same input, same output. Yeah, that same input, same output. Reproducibility. So reproducibility is okay. No matter what day it is, no matter what system it is, the hash function that you use is always going to be consistent. You feed in the same input, it's always going to give you the same output each and every time. You're not going to have like a day where one day the input, like let's say your input is a string baseball, and then the output one day is different than the other. That's not good. Number three. Then another important property of a hash function is uniform distribution. What that means is uniform distribution means it's going to be, the hash values are going to be all spread out. Because one of the things that you don't want to have is things to be too predictable. If anything that's too predictable, it's going to be broken really quick. Okay? So the values are going to be spread out. Okay? And uniform distribution is going to be some randomness, not predictable. Number four, this is important. Okay? Can't go backwards. Can't go backwards. You can't go backwards as there's no decrypt function. There is no function where you can feed in the hash value and then you get back the original input. No. So that's why in cryptography these are called cryptographic hash functions. Now these cryptographic hash functions serve many extremely important purposes in day-to-day computing. Really, cryptographic hash functions, okay, I'm going to add the word crypto. Cryptographic hash function has all these properties. There's no collision, same input, same output, uniform distribution, can't go backward, and they're cheap and fast to compute. Okay? Okay, so the question is, okay, complex enough to guess from the, yeah. Yeah, that's, okay, now you can put that. I can see why it would be useful for password storing, but why do we need a hash function to be non-reversible for a hash table? For a hash table, okay, that's a good question. The only thing is to be non-reversible for a hash table. That's a different story. For password storage and for security purposes, it has to be you can't have it reversed. Okay. However, there are ways to get around that. But for a hash table, let's not worry about that today. Okay. So hash table are a little bit different because they're used for searching purposes, not so much for in this context of today. I mean, it's a good question. Explorer 88 hash table, totally different matter. But we're talking about the general idea of a hash function that you use in a hash table, which is ideally the same thing as cryptographic hash functions. Now, cryptographic hash functions in the real world are used for largely for the I in the CIA triad. The I in the CIA triad is integrity. Okay? Cryptographic hash functions are used to for integrity purposes for digital signatures. Okay, there are many different types of hash functions out there. There are many different hash functions out there, and one of the things I will do is I will do the most rudimentary hash function called MD5, and I'll just do a search for MD5 calculator. It's a website I like to use all the time, which is md5calc.com. Yeah, this one I love. I love this one. And this is a calculator for that you can choose many different hashes, hash algorithms. There's MD2. The most famous ones are MD5, SHA-1, SHA-256, SHA-512. Those are the real famous ones. So I'll give you an example. Let's do a few examples. Let's start off with MD5. Let's do a string to encode, let's say football, and let's encode that. So that means the MD5 of the string football is this hash value. Okay. Now if I do another string to, let's say Twitch, I encode that. There you go. So the MD5 of Twitch is going to be this value. Now, if I do football, all caps, with a capital F, I'll encode that. And you notice that case matters, okay? Also, if I do football 1. Now, is football lowercase different than football 1, all lowercase? And the answer, of course, yes, because there's an extra 1 in the string football. There you go. So as you can see, we've computed the hash value of 4 different strings, okay? Football, all lowercase, Twitch with a capital T, football with a capital F, and football 1. So there's a couple of important properties that you can see here. Case matters, case-sensitive matters. Adding or removing one character makes a huge difference to the hash value, okay? And also, as you can see, all these hashes, all these MD5 hashes are all unique for each unique input, okay? So you may be wondering, what's the difference between MD5 and other hash algorithms, let's say, for example, SHA-1? Well, let's calculate the SHA-1 of football, lowercase f. And you can see that this is now the hash value. It's not only that the algorithm will produce different hash values, but the most important thing is going to be key length, okay? And they're all consistent as well, too. You can now see the key length for SHA-1 for any input is the same. SHA-1 for football 1. Okay. Yeah, and so you can see the hash values are different and also longer. Does longer mean better security? The short answer is yes, absolutely. Okay, let's do SHA-512. SHA-512 of football, all lowercase. You can see the key is much longer. Okay, Twitch. Okay, let's go capital football and football 1. You can see what they called the hash value. This is also known as checksum as well. So the hash value, the resulting value, is also known as a hash value, or it's also known as a checksum. Okay, so you can see I calculated 4 different strings using 3 different types of algorithms: MD5, SHA-1, and 512. SHA-512 is a lot longer than SHA-1. It's a lot longer than MD5. So I'll give you, so you may be wondering, okay, all right, so this is nice, but where am I going to see these hash values used? Okay, let me give you another practical example. Anyone here verify the integrity? I'm sure you all download software, but do you ever verify the integrity of your software? How are you so sure that you really downloaded the correct software? Or if you have fully downloaded the software? Now, back in the heydays, I didn't do this. Now, it's a must, okay, to verify the integrity of your downloads. So I'll give you an application of checksums, cryptographic hashes where this is used. A good example is VLC. VLC is an open source media player, probably the best, yeah. Mainly for verifying ISOs, files like Linux. Yep, absolutely. Distros, firewall will delete event. Yep, absolutely. Nice student, KFarm. Absolutely, you're correct. It's not just Linux distro. It's any software download. A good example. I'm just going to give you a hands-on one. Yeah, firewall will delete wrong software if downloaded. Yeah. I'll give you an example. Let's download VLC. VLC is an open source and an extremely awesome media player. It can play any sorts of media files um, around, basically. So here I'm going to go and download VLC for. I'm just going to click on the download button. And watch what happens. It's going to download. It's going to download. Up. Here we go. I'm going to save it to my desktop. But what's important is, well, we'll let it download. But you see, there is a line here. It says display checksum. I want to actually click on that. This is now, hopefully by the end of today, you'll get into the habit of verifying your software downloads. Some software like Homebrew will check the checksum for you automatically. But if you want to learn how to check the integrity of your download by hand, I'm going to show you. So here it says, SHA-256 checksum, 99C, yada, 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 all the way up to 8F47. So what this means is, okay, what I need to do is I need to feed in my download, which is, here it is on my desktop, VLC, okay, VLC, that 3 point, how big is this file? 48.84 megabytes. So what I will need to do is I will need to send this file to a program called OpenSSL. Use SHA-256 as the hash algorithm, and hopefully that the output will be 99C, yada yada, all the way to 8F47. So I'm going to open up my terminal right now. And you can see I have the download, VLC-3.0.18. So what I am going to do now is verify the checksum of your download is OpenSSL. This is the hand way. Put in your algorithm, your hash function algorithm, which is SHA-256. And then the name of your file. And here you go. And you can see it's very fast. And you can see that the SHA-256 VLC, that the DMG file comes out to be 99C all the way to 8F47. Does these match? And the answer is yes. Okay. Then the answer is we have downloaded VLC 3.0.18 from Mac OS for the Apple Silicon correctly. Now what happens if your checksum doesn't match? What happens if, let's say for the sake of argument, I calculate the SHA-256 checksum of this file and I got a different result? Well, that means one of three things. Number one, that you have an incomplete download. Number two, you downloaded the wrong file. Or number three, this one can get really bad, and I've seen this before, is you probably downloaded a laced or improper version of VLC 3.0.18. That means it's probably a binary that got laced with other stuff on here, like spyware and malware. So that's why checking the integrity, checking the checksum of your download is extremely important. Because you want to make sure you downloaded the right thing and you downloaded the entire file fully. This is extremely important for bigger files such as like Linux distribution DVDs, which are like over 3 gigs. Okay? Here it is. SHA-256 will hash the whole file or just this. Oh, no. The whole file. The whole file, nice student 09. The whole file. So if I go and modify like one bit of this file, the checksum will be different. Oh, yes. Yes. Not the string. No, 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 no. If you want to do that, well, not that, definitely not the string. Here, the whole file. Here's your proof. I'm gonna copy the whole file. So now, if I do a SHA-256, the hell? SHA-256 of the string VLC that 3.0, yeah. Watch what happens. The output is gonna be 2EF3C19. Does this match? Nope, doesn't match. No. So, no, it hashes the entire file, the whole file. Okay? So now let's take a look at, the idea of what we learned. Now let's use checksum. Let's use a cryptographic hash function. Remember this example that we have been doing. Now, instead of storing the password, well, we'll just store we're going to store the cryptographic hash values of the plain text password instead. So now let's improve this this data set right now by using cryptographic hash function. And we're going to use SHA-1. We're going to use SHA-1 as our hash function. So I'm going to do a SHA-1 of eat more chicken. SHA-1. And the value is BD yada yada yada. Okay. And we're going to calculate now the SHA-1 of E equals MC2. We're going to calculate the SHA-1 value of money is the most important thing in the world. We're going to do a SHA-1 of the string ABC123. We're going to do a SHA-1 of the string password. We're going to do a SHA-1 of royalty. And we're going to do a SHA-1 of ABC123. Didn't we do that already? Yes. And there we go. All right, so here is our design, our next iteration of storing usernames and especially passwords. Here we go. So now, does this look a little bit better? Okay. Well, yeah, it does. Well, the big problem we've solved is we've solved one big problem. Now, if you take a look at this, the storage of username and passwords, this is kind of nice. The passwords are not stored in plain text. That's great. But what's the problems? Tell me one or two problems. I can name at least one. But what's wrong with this design? And this is wrong way number 2 of storing passwords. This is not good enough. There's still some things that are horribly wrong with this. Again, we're just storing the cryptographic or the SHA-1 hash value of the passwords. Hash doesn't include you. Nope, no. Hash, that doesn't matter. Hash doesn't include username. Nope. Hash, we don't need. We need the username for all sorts of different operations. No, we don't ever hash the username because then it will be just way too difficult to do any operations on a machine. Okay, so Flacaba, absolutely. Okay. Think osculate, that's a good one. Every MC equals empty squared looks the same once hash. But we got a couple problems here. Problem number 1 is what SHA-1 is no longer secure. That's issue number 2 that I had on my list. But there's a more glaring issue here, though. There's a more glaring issue. Take a look. Take a look at the passwords. Do you notice a pattern? Do you notice something? I'll give you a hint. Remember how I said about one of the important properties of cryptographic hash function is there's no decrypt. You can't go backwards. Well, the problem number one is, okay, it's nice that we're not storing the plain text of the password, but if an attacker gets a hold of all this list of username and password hashes, the attacker will notice Data Guru and X Baker share the same password. That is not a good thing. And how many people around the world use the same exact password for a given system? In other words, how many people do you think use ABC123 as a password? Too many. So now the problem is an attacker will just notice, I see that Data Guru 18 and X Baker are using the same password because well, look, the password hash is the same. That's issue number one. Okay? The issue number one is if you're storing just a plain hash of a password, okay, the straight cryptographic hash of a password, in this case SHA-1, you can identify who's using the same which people are using the same password. In this case, it's Data Guru 18 and X Baker. Issue number two. Issue number two is the issue of weak passwords. Oh well, issue number two. Let me get to Flacca's point about SHA-1 no longer secure. Here's the thing. While you can't actually decrypt hashes, there's no function to take in 6367 yada yada all the way to 5EE. Problem is, people around the world have already pre-computed the cryptographic hash of every single dictionary word and common password. I'll give you an example. If you let's go to Google for example, and you type in, you do a search for 6367 yada yada the hash value, and you look it up, you're going to actually see results. Okay, and here it is. The SHA-1 hash 6367C4 was successfully reversed into the string ABC123. Again, while there is no such thing as a decrypt function in a one-way cryptographic hash, people have already pre-computed the cryptographic hash of every single dictionary word. Okay? Okay, a stall fee, we're going to get to, okay, you jumped the gun. You jumped the gun for a second, all right? So that's problem number three. All the common dictionary words, I'll just give you another one. I'll just give you another idea. Let's do, what's the SHA-1 of baseball? I mean, people have done this all the time. If I do a search for this SHA-1 hash, yeah, we'll successfully reverse into baseball. Okay? Okay. So a store fee will get into your issue later. But I want to go to Flacca's comment that SHA-1 is no longer secure. That's also another big problem. Okay, MD5 and SHA-1 are now known to be broken. What does that mean? Known collisions. And I want to show you this, the work that Google did back in, 2017? Shattered. Google did this. We've broken SHA-1 in practice. The industry cryptographic hash function standard is used for digital signatures and file integrity verification and protects a wide range of spectrum of digital assets, including credit card transactions, electronic documents, open source software repositories, Git, and software update. It is now practically possible to craft two different PDF files, and obtain a SHA-1 digital signature on the first PDF file, which can also be abused as a valid signature on the second file. That's not good. And here's all the information out there. And here's the proof. Can I share? All right, here it is. This was in 2017, if I'm mistaken. Ideally, this is what should happen. Two different files, normal behavior, different hashes. but when you have two different documentation and they come with the same hash, the hash function is broken. Potentially impact the systems. Now here's the caveat though. It took an asinine long time to create a collision. That's a lot of SHA-1 compressions performed. Over a million, over a billion, over a trillion. Yeah. So while there is collision in MD5 and SHA-1, people still use it up to this day because it's fast for legacy systems, and it's really hard to find a collision. It takes a long time. MD5, here you go. It takes what? 110 GPUs 1 year to find a collision in SHA-1. But again, people still use it. Legacy purposes, speed, demonstration like this. But it takes a long time to find a collision. But of course, if you're having like really serious sensitive information, all right, you don't want to be using broken hash functions. Okay, so that's problem number. That's a big problem. So there's three problems with just storing the cryptographic hash. Number one, you can just eyeball who's using the same password. Number two, is a lot of the really, if you're using dictionary words or common passwords, people already computed the hash value of those. And number three, SHA-1 is broken. Okay, SHA-1 is broken. So now what do? Here's the correct way of storing passwords. Now the problem is, let me talk about a stall fees. Let me talk about your problem for a second. Let me just go all the way back now. So a stall fee, you said if the password column is hash of the username plus password, doesn't it solve that problem? The problem of uniqueness. And here's the answer. The answer is yes, but here's a huge caveat. The problem with a stall fees idea of computing the hash value of the username plus the password is too predictable. Okay, it's too predictable. Still going to be really easy because people know your username. Then if people know your username, they already know a huge piece of the puzzle. But here's that they know what token to use. If you're going to use a username as the token to make your hash more unique, it's too predictable, too easy. However, we can use that idea though. Right, if that's another, if I use the same, then yeah. But here's the other thing. However, I like where you're going with this. I like the idea of making the hash a little more unique if you add a token to it. Not just any token, but what will happen when we do a random token? Let's do what this means. Okay. So let me add a new column to this table called token. And I'm just going to add two letters. And this is all random. A1, B2, case matters. C3. Now I'm just making random token. DR, F1, PU, and of course FU. Okay. Assume that these tokens are random. But now what I'm going to do is, instead of calculating the straight hash of the password, I'm going to calculate the hash of your token plus your plain text password. So what is what I'm going to do? actually, that's not going to work. Okay, whatever. All right, so we're going to still use SHA-1 because that's what we used in the previous example. So now I'm going to calculate the SHA-1 hash of eat more chicken, but prepend an A1, the token, beforehand. I'm going to now calculate the SHA-1 hash at E equals MC2, but prepend the token B2. So everyone is assigned a unique token. I'm going to calculate the hash of C3, the token, plus money is the most important thing in the world. Okay, I'm going to calculate the hash of the token plus the password, in this case is DR plus ABC123. It's a random token. F1 and password. There you go. PU and royalty. So yeah, a stall fees idea is running a little bit into fruition, and the last but not least is FU ABC123. Yay. Here you go. I'm going to copy this one. Alright, now this looks good. Now this is the correct way of storing usernames and password hashes. Now if I try to do a Google search, I was opening up, let me open up a new tab, go to Google, and punch in this weird hash, 402, and let's go for results. We don't get any results back. Yay, that's good. Okay, then that's good. So now, okay, do these cryptographic hash look really unique? Yep. Is there a way that we can see that Data Guru 18 and X Baker are using the same password? No, different password hash. So we solved the problem. Yeah, so this looks a lot better. This looks a lot better. And in fact, this is actually how usernames and passwords are stored on systems these days. This is like the ideal way of storing usernames and password hashes on systems. This is what Linux uses in most production systems. But now I want to formalize something. Remember, I've been using the word token. This token, I've been using the word token this whole time. But there's a more formal term for token, which is to add randomness to the password hash. This is better token. It has a better and more formal name, better known as assault. S-A-L-T, assault. And so what's the point of assault? Of a password salt? Okay, salting password 101. Aha. Can someone help me? And this is a Stack Overflow post. Okay. Validate. So can someone help me understand how salting works? So if I understand that, understand value, yada yada yada, gonna intensity, yada yada yada. How do we salt? Okay, so here it is. Salt is combined with the password before hashing. The password and salt clear values are concatenated and the resulting string is hashed. This guarantees that even if two people were to have the same password, you would have different resulting password hash. It also just makes attacks known as dictionary attacks using rainbow tables much more difficult. Here it is, another thing. The salt is then stored in the original / clear format along with the hash result. Then later, when you want to verify the password, you would do the original process again, combine the salt from the record with the password the user provided, hash the result, compare the hash. And there it is. And so this idea of cryptographic hash with the password salt is now used as a standard. Okay, so Now we've talked about the right way of how you actually store usernames and password hashes along with the salt. So now you may be wondering, okay, can I actually see this in practice? And the answer is yes. Now let's talk about how, well, usernames and passwords are stored on a Linux-based system. Okay? Alright, so now what I am going to do, I don't think, I'm still going to leave the browser open. I don't really need this anymore. And I can do an RM star. I can do an RM star on my desktop. I don't need this anymore. I do need the terminal. And now let's actually have an understand. I do need the web browser. Let's have an understanding and let's take a look at how username and password hashes are stored on Linux. And actually I'm going to create three users. I'm going to SSH into my Pi-hole. Yeah, and I'm going to create a couple of users. Who do I want to actually have for user? A stall. Okay, so I'm going to use that's what I'm going to do. Okay, so I'm going to create 3 users on this system. Sudo add user. So who wants? I'm going to use Think Osculator. Are you there? I'm going to add a new user to my system called Think Osculator. Think Osculator. Your password is going to be... I'm not going to tell you what it is. Okay, there we go. Good. Yeah, it looks good. Okay, so I need another user. Nice student 09. I'm going to add user nice student 09 to my system here. Your password is going to be... Oh, yeah, I want to try again. Yeah. All right, and I'm going to add one more user. I'm going to add one more user. KFarm03. Yeah. KFarm03. Your password is going to be... Not telling you. Yeah. All right. Excellent. So now I've created not 1, not 2, but 3 brand new users on my system. On this Linux system. KFarm, Think Osculator, and Nice Student 09. So now you may be wondering, well, 2 questions. Number 1, how are usernames and password hashes stored on a traditional Linux system? That's question number 1. And question number 2, of course, is an obvious one. What passwords were they? Okay, I'm going to clear my screen. So first and foremost, where usernames and passwords are stored on a Linux system is in this file, cd/etc. Okay, in my et/etc directory, and the name of the file is passwd. Yeah. Cat is readable to the entire by everyone to the world. Cat passwd. There you go. Here you go. You can see at the end of my /etc/passwd file. You can see my 3 users, Think Osculator, Nice Student 09, and KFarm 03. There you go. It's your username, that's your password hash. There it is. Wait, what? What's the problem? The problem is, you may be wondering, wait a minute, I see username, but I don't see anything that closely resembles a password hash. That's correct. Back in the ye good old days, I mean, we're talking about the early 2000s, the username and the password hash were right in one file, /etc/passwd. Then, of course, later on, what they just said went, okay, this is not a good idea to actually have mix both the username and the password hash into one file. Decided to separate it out. And that's where Think Oscillator actually have said. What happens now is that the password hash is now in a separate file. It's in a different file, /etc/shadow. So if I do a man passwd, oh, let me clear the screen. Man /etc/passwd. Did I get man page? Oh, yeah. Shadow password file. Shadow is a file which contains the password information. Here it is. Shadow is a file which contains the password information for a system's account and optional aging information. This file must not be readable by regular users if password security is to be maintained. Okay. What are these users able to be? Well, that's the thing. What are these users able to do on your computer? That's a good question. And I set it up where these users get just regular users. They're not root. They're not root. SK Potato. That's a good question. So these users are just regular users. Okay? They can log in. They can have their own. They have their own home folder. That's it. Now, let's do a more /etc/ oh, actually, sorry. Let's do cat /etc/shadow. Oh God, permission denied. And so here is now I have to do a sudo cat /etc/shadow. And here it is. Now this looks a little different. We see the username, and now we see the cryptographic hash. I see Think Oscillator, Nice Student 09, and KPOM 03. They're just regular users. So now your question is, okay, wait a minute. Didn't we just talk about password salts? Didn't we just talk about hashes? So how the hell do you read and understand a shadow file? How you understand a shadow file is this. Let's bring up the documentation. I like this one a lot. Understanding the /etc shadow file. Let's have an understanding. Alright. There are several different authentication schemes that can be used on a Linux system. The most commonly used in the standard scheme is to perform authentication against the /etc/passwd and /etc/shadow files. /etc/shadow is a file that contains information about the system's user's password. It is owned by the user root and group shadow and has 640 as file permissions. So here's how the format. This is the important part. Contains one entry per line, each representing a user account. You can view the, okay, this is what we just did. Typically, the first line describes the root user, followed by the system. Okay. This one. Each line of the /etc shadow file contains 9 separated fields. The most important ones are the first two. Now, the first one is, the first field is the username, followed by a colon, which is then the encrypted password. Okay. The password, the encrypted password. The encrypted password is shown to say is in the following format. $type, $salt, $hash. $type is a method cryptographic hash algorithm and can have the following values. $1 is MD5. $2A is Bluefish. $5 is SHA-256, and $6 is SHA-512. If the password field contained an asterisk or an exclamation point, the user will not be able to log into the system using password authentication. Other login methods such as yada yada, okay? So, take a look. So now let's think of Think Oscillator. Let's take a look at Think Oscillator, okay? Your hash is all this, okay? Starting with $6. So let's take a look at the documentation that we just had. $6 mean SHA-512. So the hash algorithm is SHA-512. So Think Oscillator, Nice Student, and KFarm03's password are stored using SHA-512. So the 63 all the way up to the 7. So here is the algorithm, $6, followed by the salt up to the $, and that's the hash. Okay. $6, followed by this, which is the salt, followed by all this after the $, all the way to the colon. Well, that's the hash. KFarm, that's the salt, and that is the password hash. Yep. $type, $salt, $hash format. Okay. So now you understand how usernames and passwords are stored on Unix system, and also ultimately a little bit about how password authentication is used on Linux. So now let's talk about breaking the passwords. So what's the password for, or let's think of it, say this for an argument, what happened if Think Oscillator, Nice Student, KFarm03, if they've lost their password? Well, now let's do some password recovery, or password cracking. So how do we crack passwords? Well, we definitely need a shadow file. But I want to actually now introduce you to one of the most famous password crackers in the world, and one of the oldest in the world. And that's called John the Ripper. John the Ripper, free and open source. John the Ripper password cracker is available at platform independent. John the Ripper is an open source password security, auditing, and password recovery tool available for many operating systems. John the Ripper Jumbo supports hundreds of hashes and ciphers, yada yada yada. Again, John the Ripper is free and open source. It's also relatively simple to use, and it follows very much what we've been talking about this whole time with shadow and PASSWD files. It's generally fast as well. Okay, it's generally fast. So if you're on Mac OS, how you would install John the Ripper, you will install you can use Homebrew, and you can install John the Ripper by way of brew install John space Jumbo. If you have Homebrew on Mac OS, it's brew install John-Jumbo. And this will give you, here it is. And it says John Jumbo 1.9.0 is already installed and up to date. There you go. Alright. So we want to be using a fast computer for password cracking. Now, I'm going to be using my Mac for password cracking. But there's a few steps before we actually, so how you run John the Ripper is really it's really simple. Once you have John Jumbo or John the Ripper installed on your system, you just type in John, followed by the name of your crack me file. That's it. Here it is. John the Ripper 1.9, there it is. Now, we need to create the file that we need to feed John the Ripper into. here we are, and we're on this Linux system here. So I'm going to go back to my home directory, and I'm going to clear the screen. My home directory got no files. What I need to do is I need to make a copy of 2 files. The /etc/passwd. I need to make a copy of that to my home directory, and I also need to make a copy of the shadow file. So I need both files. /etc/passwd and /etc/shadow. So now I got a copy of both of them. What I want to also, just for sake here, I want to change the owner of both of these files to be me. Okay. There you go. You need both the /etc/passwd and /etc/shadow. Oh, sorry. The local version, okay. Got the one in my folder, that's fine. Now you have both files. What we need to do is we need to concatenate both of them. We need to concatenate both the password and the shadow files that we just have a copy of. John the Ripper comes with a utility called unshadow. Man unshadow. Unshadow combines the password and passwd and shadow files. Okay? The unshadow tool combines the passwd and shadow files so John can use them. You might need this since if you only have yada yada yada. Okay. So how you do this is how you combine, concatenate both the passwd and shadow file using unshadow is, well, unshadow, passwd, shadow. There you go. It gets spits out to the screen. But the problem is we want to save this to a file, not just output to the terminal. So what I do instead, what I have to do is unshadow, passwd, and shadow, and I'm going to send the output to a file called crackme.txt. There you go. So now if I do a cat crackme.txt, there you go. You have a concatenation of both the passwd and shadow files. Alright, that's good. And so we can now feed in this file, this crackme.txt, to John the Ripper. Now, the only user account I really want to crack are ThinkOsculator, NiceStudent09, and KFarm03. So I can actually just modify crackme.txt and delete all the other fluff. Up to until ThinkOsculator. So we only got 3 accounts to crack. Okay. These are our 3 accounts. Alright, we're going to take some bets here. Anyone want to take a guess what the password of ThinkOsculator is, NiceStudent09 and KFarm03? Anyone? I need, you can exit out of here now. And now back on my Mac, so I'm going to go to my desktop. And now I am going to do a download. Okay. So I'm going to do a download using SCP. Save it to the desktop, and here you go. I got a copy of it, crackme.txt. Then I'm going to do code crackme.txt, and just for our purposes, I don't need this demonstration anymore. I'm going to copy. Oh. I'm doing that right now, ThinkOsculator. There you go. Alright, so now I got the crackme file. So how you run John? Okay, we're going to take bets now. We got 3 students we're going to crack. 3 people we're going to crack. Think Osculator, Nice Student 09, and KFOM 03. To actually send this to, so what we're going to do now is the following. We're going to crack these password hashes by way of John the Ripper. How you do that is this. John, crackme.txt. When I hit the return button, when I hit the return key on my keyboard, what's going to happen is John the Ripper is going to start cracking the passwords. No order. In no particular order. It's going to use the internal word list of John the Ripper first. There is a word list built into John the Ripper. It's going to use that first. Then, if that fails, it's going to go brute force. There we go. Let's go. And, woo! Woo! We got a winner. Yeah, we need a gift. We need to give Jack Iceberg 21. We need to give Jack Iceberg 20. We need to give Jack Iceberg 21 a prize. He guessed correctly. He guessed it. ABC123 is the password for Nice Student 09, and capital PASSWORD, capital password with a capital P, I think Osculator. So it came pretty quickly, but we're down to one person. We don't have the password for KFOM yet. So now it's going to go brute force. So the real easy, these days, if you're using, what is it? I'm just going to, okay, by the way, if you want to crack a password, one password, you got to have these up and running for a while. So when you're cracking passwords, as you will be, for the semester long, for the 1-month password cracking contest, which is now open. Okay, this is the annual password cracking contest in this my security class. There you go. Okay, make sure it's not going to be immediate. There are there's 16 hashes. Crack as many of them as you can. If you actually crack, here's the rule of this contest. If you actually crack all 16, you get an automatic A in the course. By the way, no one has ever done that before. You got 1 month to start cracking. Okay? There are 2 sets of hashes. Crack as many as you can. Now make sure the important point is you don't want to run these just, you gotta have your computer run for a long time. We're talking hours. So get a password cracker running, let it run, go out for coffee, for a drink or something, or go out for a walk. Okay, so the problem now is that the password of KFOM is, we're still trying to crack that. Now it's going with incremental mode, as you can see. I'm going to hit Control C. Now, once you do a Control C, you can actually quit out of a password cracker and you won't lose, and it will actually continue off where it was. In fact, you can actually go to your home directory, and there is a hidden .john folder, and this is where you actually can see like your log file, like what John was doing. Okay, this is a long file. You can see the pot of all the cracked passwords. You can see the pot of cracked passwords. And I think, well, I don't know what the rec is. Records. Okay. But to really, really speed up, I want to let you all know. Do it just for your humor. Take a look at the worst passwords. Do a search for the year and the worst password. Here it is. 2022's worst password. Don't use any of these. Sadly, this year looks just like every previous year. Yeah, well, no shit. It's always the same shit anyway. ABC123. Is it on here? No. QWERTY 1234556 password. There you go. Here's your words. ABC123. Yeah, number 15. There you go. Always listed. Same stuff. Same old, same old. I'm getting too old for this shit. Here we go. These, and guess what? Every year's the same stuff. So here's the thing. To really speed up your password cracking, your best idea is to use word list. And I want to introduce to you my favorite collection of word lists called a Daniel Meisler SecList. This is a free and open source resource. SecList is the security tester's companion. It is a collection of multiple types of lists used during security assessment collected in one place. This also includes like username, password, fuzzing payloads, sensitive data patterns, shells. Take a look at passwords. And these, here we go. We have this is a nice collection of word lists for password cracking. Some files are a million lines long. I'll show you. And I always, and I mean always, have a list. I have a copy of SecList on my computer. And I just want to just in here's a list of all the password lists that are on SecList. Dark Web 2017 Top 100. There you go. It's only 100. Yep. How about 10,000? Yeah, there we go. Ronaldo. What a fraud that guy is. Fucking fraud. There you go. There you go. That's what you call wordless. They tied today. What the hell is this shit? They have this on us? Okay. Interesting. Heard it was a great game today. Didn't watch it. Dark Code's one of my favorite. Okay. If I do a word count, yeah, this has over a million words. All right, so how do you actually use a word list with John the Ripper? All right, so where am I? Okay, where am I? I'm going to bring up a new tab. Ah, shoot. I'm going to bring up a new tab. Desktop. And you want to run John the Ripper using a password, we're using a word list. Is John minus word list equals and the path to your actual list that you want to use. I'm going to use that one, Dark Code. I just go run through this list. Oops. So the way you crack password, use word list. So now I'm going to use a word list with John the Ripper. The word list is going to be Dark Web 2017 top 10,000. And let's see if K-Farm password can be cracked now. That is. The real trick is to use word list. Whenever you do word, so when they did so it's not in one of those. Not in one of those. I'll let you have fun though. So what story do I want to tell? When they cracked, when they did they hacked LinkedIn back in like 2012. When they hacked LinkedIn, and they got like millions, like we're talking tens of millions of record. 60% of all the passwords were cracked. Password hashes were cracked, like within like 30 minutes using wordless. Okay, let me think. Let me do a search for it. LinkedIn breach. Here it is. Hackers cracked more than 60% of breached LinkedIn password. This is a little old. Yep. Back in June 2012, more than 60% of unique hash passwords that were accessed by hackers from a LinkedIn password breach were posted online, yada, yada, yada. It's very likely have also been cracked. In total, 6.5 million hash passwords believed to belong to LinkedIn were posted on the Russian forum, yada, yada, yada. Based on the 118 megabyte password dump, close to 3.5 million, a unique password has been cracked and made available in plain text last night. It was only a matter of time before. All right, so this is an important point. I did not prepare for this one. Okay, it's only a matter of time before remaining passwords are similarly cracked using automated password guessing tools like John the Ripper. The speed at which so many hash password cracked were underscores the weakness of password protection scheme used by LinkedIn, yada yada yada. Actually fucked up. Wow. Okay. The breach of LinkedIn members' password are all hashed or masked using a hashing protocol known as SHA-1. Well, interestingly enough, we talked about this. Again, I just pulled this out of my head today. Yada yada yada. Interesting. So, interesting. The one point I want to make is, and this was my final message, and then that's all for today. Look, folks, an important point is no matter what password you're going to use, it's going to be broken into. It's going to be cracked. I'll say this important point. Password will be broken given enough time. And there's a point, there is a post I love to show to people. This is an old Reddit post from Data is Beautiful. Yeah, I love this one. This was 2 years ago. What is it? This was where was it? This was on Data is Beautiful. The time it takes for a hacker to crack your password. So the number of characters, and then of course a different class. If you're only using numbers only, lowercase letters only, uppercase and lowercase letters only, numbers, uppercase and lowercase letters, numbers, uppercase and lowercase letters, and symbols. If it's only like 4 or 5 characters, it's gonna be broken instantaneously. Now, look, if you're only using numbers only, if you're having number of characters 18, it's going to be broken in at most 9 months. Probably a lot quicker these days. Lowercase letters, yada yada. But, as you can see, the worst case is if you're using an 18 character password with numbers, uppercase, and lowercase letters and symbols, it's going to take 7 quintillion years. We might see the second coming of dinosaurs by then. But it doesn't matter if your password, look, it doesn't matter. It could take maybe instantaneous, as we just saw with ABC123. It could take instantaneously. It could take 1 second. It can take 1 minute. It can take 1 hour. It can take 1 day. It can take 1 year. It can take 1 decade. It doesn't matter what it is. Yeah, it doesn't matter. It's only going to be a matter of time. 1 second, 1 minute, 1 hour, all time. 100 trillion years is still based on time. It's still time. Your password can always be cracked, given enough time. So what option do you have? Really, the problem is every system uses passwords these days. That's why knowing the fact that password can be broken, and actually these days it's probably more easier than you think because so many people reuse passwords. Your only defenses are 2 things. Number 1, use a password manager. Invest in one. I don't want to I use Bitwarden, but you can use any, but definitely get a password manager. It's a really, really good investment for yourself for the long run. And also, the other thing is use 2-factor authentication. I use 2-factor authentication for everything. So even if they do end up finding your password or they crack your password, they need to have that second key or the second door to really get into a system. So other than that, folks, yeah, I'll let you all actually try to crack KFarm03's password. But other than that, happy hacking, everyone. See ya. Yeah, the stream's available. The one's not on Twitch now. Nope, it's only Twitch, and then this also gets exported to YouTube as well. Yep. See ya.